Okay. Stop looking at our stuff. You have work to do. Okay. Let's go back and look at the smooth muscles that are there. What smooth muscle is, and just pick it up because we're going to complete that relatively quickly here. I should hope. So again, the consistent finding around hollow tubes, longitudinal and deep to the longitudinal, closer to the opening of the lumen, circular smooth muscles. And again, the whole idea of alternating contraction and relaxation, effectively pushing, compacting and pushing, compacting and pushing, which is important. The fibers are relatively small, relatively short, somewhat bulbous in the middle, totally different shape, wider and these are wide in the middle and narrow at the tips, and not anywhere near as long. And they're typically mononucleated. Exceptions would be very, very. Okay, only endomysium, not that whole elaborate sheathing. No neuromuscular junction, what they call diffuse junctions. Points of distinction are where questions come from. So the question is, in smooth muscle or in skeletal muscle, is the first part of the question. I mean, you underline that, you highlight that, because now your answer is always based on that. So, where is neurotransmitter released in smooth muscle? And surely one of and why they call wrong answers distractors is they're there to distract you. It will be neuromuscular junction. Ain't got one. So the answer is diffuse junction. So they have varicosities, their autonomic nervous system. We get to autonomic, very limited, is typically acetylcholine or norepinephrine that's released. So you will see these are, particularly in blood vessels, would be norepinephrine based that are there. The varicosities are the enlargements. Yes, they have synaptic vesicles. Yes, they have mitochondria, but they release it more directly in. So they do not have the elaborate endoplasmic reticulum. They do not have T tubules. They do not have troponins and tropomyosins that are there. It doesn't store intracellular calcium. Most of the calcium, as we commented on, was extracellular. And then these infolds, these caveolae, and we touched on it a little bit for those that weren't here. Was everybody out? Is this like a I'm not coming day today? Where are your? She didn't come in, and you're out partying. Caveolae contain numerous calcium channels, and this is where we get into the calmodulin. Calcium, extracellular calcium, as we talked about a little bit for those that weren't in the MCAT portion of the program. The calmodulin is a binding protein that changes shape and triggers other proteins, typically kinases, to generate activity. Here's the drawing. Calcium here, so these are, again, voltage-gated calcium channels coming from the release of neurotransmitter, more inside-based than outside-based is where the control is. And then in the sarcoplasmic reticulum, we also have calcium channels, and their entry is triggered calcium release from the sarcoplasmic reticulum, which is limited at best. That's there. Smooth muscles are electrically connected. In this case, gap junctions. So it's a little bit different. You're going to see gap junctions in cardiac, but you don't see those gap junctions per se in skeletal muscle. So they're electrically isolated. Gap junctions are those connexons, those protein passageways. Sometimes they allow electric charge particles. Sometimes they allow other substances to communicate. There are no striations, no sarcomeres. Striations there's overlap, but the fibers are not visible. They do contain overlapping thick and thin filaments. The ratio is roughly 12 to 13 or so to 1 of thin to thick. So thick filaments are fewer, have myosin heads along their entire length. Again, 1 to 13 versus roughly 1 to 2. So thick filaments, heads along the entire length, making smooth muscle as powerful as skeletal. It just does not do so as rapidly. And again, overall power has to do with the speed of contraction as well. But these are much more suited for long-term usage. They there's power and strength. I don't think there's nearly as much when we talk about the ability for skeletal muscle to do chores. And on the smooth muscle, they function constant. They're not so much constantly, but they can do so uh, almost continuously without tremendous amounts of relaxation. And cardiac is sort of the hybrid, where it has power, strength, and endurance all together. So that is almost more remarkable. No troponin per se. It does, correcting myself, contain the tropomyosin, but not the troponin. Troponin is really the control. The tropomyosin, again, still is a regulatory, but the calmodulin is the protein that binds. And so here we get to look-see. The analogy to the compartments are called dense bodies. You can see the gap junctions are there for communication. The dense bodies act more like a boundary, if you will, allowing this sort of spiralized intermediate filaments to facilitate the contraction. Multiple caveolae. So the thin and thick filaments, rather than being arranged in a linear or parallel fashion, are much more diagonal or spiral arranged. So it corkscrews. So it twists. And when doing so, you're going to see it changes. The lattice-like arrangement of the intermediate filaments are there to resist tension. The dense bodies anchor. And the Z discs, really, for lack of a better way to describe it, are anchors. And during contraction, the sarcolemma between the dense bodies bulge outward. So it looks like that. You can see the difference. It spirals and it creates sort of this wider or bulged area centrally, less so. It's just sort of like twisting something in that regard and getting sort of something that has the capacity to bulge in the middle. And you've seen this illustration before. And all of that. Slow, synchronized contractions, which is very much different, I think, than the way skeletal muscle is. Coupled gap junctions, action potentials transmitted to fibers. Some are self-excitatory. So we have ways that it's sort of like what occurs with peristalsis. It pretty much is always occurring. It's just a matter of how, when you eat something, it has a variety of stretch and chemical receptors that really stimulate the food passageway. And also those stretch receptors will, let's say in digestive, it will release chemicals that will augment that activity or trigger certain areas of activity. So it's a well-organized kind of a function. So there are plenty of these that have a pacemaker-like effect, and that means that the stimulus just occurs, okay, periodically. And the only thing you control is the rate. So you can make it more rapid if necessary or slow it down if necessary. So that's self-depolarization. So it's similar to skeletal muscle by this. Actin and myosin interact with sliding filaments, okay. The final trigger is calcium, okay, is increased in intracellular calcium. So there is some calcium that goes into the cell. ATP is obviously part of the process. Contraction stops when calcium is no longer available. All sounds the same. The calcium is still obtained from a sarcoplasmic reticulum. There's some in there, but nearly all of it is extracellular. It has troponin's not there. It binds to the calmodulin. Myosin kinase is something that's unique to that system. That's what the calmodulin triggers a shape change in. The activated myosin kinase then phosphorylates the myosin head, activating it. Cross bridges occur. So we know kinases phosphorylate. That's their job in life. Phosphatases dephosphorylate. Stopping smooth muscle contraction requires more steps rather than skeletal muscle. Calcium has to detach from the calmodulin. Transportation of the limited amount of calcium back into the sarcoplasmic reticulum, mostly being pumped out of the cell. Dephosphorylation of the myosin to inactivate the myosin. And they just go through the steps here. So those are the bases that you need to know. Calcium binding, activating the calmodulin. You can see the calmodulin changes shape. It then activates the kinase molecule, those light chain kinase molecules, and then they in turn, again, assisted by ATP, phosphorylate the heads and create the activity. Slower to contract and relax, maintains it for long periods of time, little energy cost. So they're more about having increased degree of duration. It's a different kind of contraction. The ATPases are slower acting. Myofilaments can hold each other together to save energy. So there's a moderate degree of contraction constantly. So they have their own smooth muscle tone. That's there. So, I mean, they're different systems, but they're both integral systems that we look at. Nerves certainly control it. Hormones certainly control it. Local chemical changes. The local chemical changes are a big deal. I mean, you're going to see a lot of that in digestion that's going to occur. And like a lot of these systems, changes in acid and base levels certainly also play a role. Neurotransmitter binding causes local or action potentials, depending on what it is. Really, again, you have the same thing here. They're just characterized as graded potentials. Increased calcium concentration in the sarcoplasm, mostly by the extracellular mean. Depends on neurotransmitter release and the type of receptor. So it depends on what organ it's attaching to. So you're going to see that really closely when we get to autonomic. And really the critical player in this, and we talked about this earlier in MCAT, is an EpiPen. It's we call a beta adrenergic receptor. It's a beta 2, not a beta 1, or not an alpha 1. So what does it do? It relaxes the smooth muscle in the bronchioles to facilitate breathing, rather than constricting. If we put the epinephrine, like when they had epinephrine, it's like when you go to the dentist and have local anesthetic, that anesthetic almost always has epinephrine. Okay. And epinephrine is there to squeeze the blood vessels tight, so it limits the bleeding, so the dentist can do it too. Dentist, oral surgeon, whatever mouth procedure is done. When we did that in feet and toes, you tended to stay away from the epinephrine. You didn't want to have somebody have an inappropriate response, and it would cause potentially enough vasoconstriction that tissue might die from the trauma of surgery. So you tended to be pretty careful using that. So most of the time, I didn't use a lot of epi in those things. We used tourniquets more than anything else for extremity surgeries. And you can use them under general and under local. So, again, response varies. One neurotransmitter stimulatory, one not. They don't have a quote unquote direct nerve supply in that regard. Okay, not all of them. So they do depolarize spontaneously. Those would be pacemakers. Responds to chemical stimuli that bind to the G protein. Chemical factors, like I mentioned, hormones. So when you're having these, we're going to revisit a lot, particularly in respiratory and in cardiac, where we have high CO2 levels or low oxygen level. What they're going to do is impact local pH. So you're going to be dealing with relative conditions of acidosis and alkalosis. Okay, and then again, a variety of chemicals. Stretch receptors are part of it. Okay, so stretch receptors, particularly in the gastrointestinal, in the bladder, same thing. Those stretch receptors are going to trigger other phenomena. As you can see, it contracts between half and twice its resting length. So they're a little bit different. Remember that 80 to 120 thing that we looked at for skeletal muscle, optimal? It, yes, how can I say it? Everybody's, let's say from a bladder, everybody's different about how much when they have to have the urge to urinate. Stomach wise, it's fascinating. Your stomach at rest is probably a couple of ounces, yet it can expand to a gallon when you really indulge, and then can go back to its resting. That's kind of what they're describing here. That's really phenomenal if you think of it. You could have somebody who had half their half of their stomach removed twice, have only a quarter of their stomach, and still eat meat, just not as much. That's why, like when I have pizza, I always get it in 6 pieces rather than 8, because I can only eat 6. Did you get that? Only cut it in 6 pieces because I can't eat 8. It's like you go to Blaze Pizza, you get 6.
Yeah.
Right. If you go like someplace else, they'll cut it in 8 or 12. I can't eat 12. Just make it 6. Blaze, I would handle one of those. Build your own. Just say. Like 3 or 4 different types of. Stop. I'm going there for lunch. Okay, the arrangement, organization, innervation, unitary, visceral muscle, everywhere but the heart, longitudinal and circular. We talked about that. The varicosities, spontaneous action potentials, gap junctions, chemical stimuli. Multi-unit, a little bit different. Okay, large airways in the lung. Okay, that are there. Large arteries would probably be a pretty good example of that. You don't see spontaneous depolarization. There's a lot more when you're looking at these larger channels, the large bronchial channels, the large arteries. They're a little bit different that are there. But I don't think I get too much into that also. So voila, we're done with muscles, which allows us to, what's he talking about? Move on. Moving on. Next chapter. This is the physiological unit of the nervous system. We did the structural unit with some physiology when we did central nervous system and peripheral from an anatomy concept. This is kind of how nerves work. And really, the idea is the differences between the terminology. In fact, there's not a neuromuscular junction, there is a synapse. We don't have just acetylcholine to deal with, or when we're in smooth muscle, acetylcholine, things like norepinephrine. Here, we're going to deal with a lot of neurotransmitters. We're also going to look at the cellular basis and pay a lot of attention to another structural unit that's microscopic. Those are glial cells. And glial cells are, and this is what we get to first, stands for the glue of the nervous system. The nervous system is so unique, it has its own connective tissue. Those are the glial cells. Rather than everywhere else, basically you're dealing with tendons and ligaments and dense regular and dense irregular, loose areolar, all over the place. Nervous system doesn't quite have that. So I think it's a fascinating system in that regard. It's what you're talking, it's certainly the master controlling system, master communicating system, and it's all about rapid. And I say it time and time again, it's an electrical system that basically does most of its in between, communicating with each other and with organs by way of chemicals. There are a lot of direct electrical connections as well. The responses are extraordinarily rapid, and they reset themselves extraordinarily. That's the distinction. As we looked at, skeletal muscle is a rapid system, cardiac is less rapid, smooth is less rapid still. Endocrine is slower than all of them, yet still in some ways rapid. So it's a matter of the degree. Same way it's set up. You have incoming and outgoing and in between processing. So you have sensory input. Again, the term for those are afferent. AFFERENT, incoming channels. Outgoing signals, efferent. They affect things. EFFERENT. And everything else we call interneurons, connectors. And the vast, vast, vast majority of nerve cells are these interneurons. They're structurally similar to one another, but it's all about the processing. It's not what you see and your reaction to it. It's how you determine that reaction and how rapidly you do that. Like I can see you're all sleeping, so I have to do something ridiculous, to get your attention. That's how it works. I look at your facial expressions or lack thereof. So we all look for barometers. Chelsea is a barometer. If she's engaged, we're all engaged. If she's not, we're all. That's a good thing, by the way. So there you are. So central nervous system, we've got the old hat, brain and spinal cord, yeah. Peripheral nervous system, everything that protrudes. Spinal nerves and cranial nerves are the things that protrude, depending where they're coming from. And it's the whole thing with axial and appendicular. Go back to the anatomy 101, axial and appendicular. That's what that's all about. That's there. You've seen that illustration. So and the divisions, we've gone over this before. It's either going to skin, muscles, or joints. We call that somatic of the body. If it's going to an organ, it's visceral. It can be motor or sensory. And when we divide the motor, we have those that are going to the aforementioned skin, muscles, and joints, or to structures we don't have conscious control. We call that autonomic. We have a whole separate chapter about that. Automatic, whatever you want to talk about. Autonomic, everything else. And the autonomic, we're going to get into two divisions. Sympathetic, which is anything but sympathetic. It's not a nice division. It's a division when you want to get into a fight with somebody. Versus parasympathetic. So before we look at the nerves, we have to look at the supporting cast. The nominees for best supporting glial cell are, they came out last night. The best supporting glial cells are the neuroglial cells, small cells that surround and wrap delicate nerve, and the nerve cells themselves. So there are really 6 neuroglial cells, 4 that are associated with the central nervous system, 2 with the peripheral nervous system. What's the difference? They can reproduce. They have a cell cycle. Okay. Nerve cells do not, since they have reached the highest level of differentiation, we do not see cancers in nerve cells. We don't make more of them. Okay. When someone has a brain tumor, it is typically in the glial cells. The most common of these is probably an astrocytoma. Most of the time, they're not cancers in the sense that they're benign, but and 90% of all tumors of the brain are benign. The problem with them is that as they grow, they occupy space and they push the brain against the wall of the skull, damaging it, tearing blood vessels, whatever, altering its function. So the astrocyte is the largest in number, has the most activities. It's the foundational cell of the blood-brain barrier. Microglia are they're analogous. They're very small, and they're really scavenger cells. They're very much analogous to macrophages. to white blood cells, except we don't see infection routinely in the brain. They're probably sweeping up little bits of damaged tissue and chemicals and things like that more than anything else. It doesn't preclude them from dealing with viruses or things, but I would think it's relatively limited. Ependymal cells are specific lining cells. The epi kind of makes you think epithelia. And the ependymal cells line the exterior of certain capillaries, and they play a pivotal role in I would say, the finalization of and distribution of cerebrospinal fluid. Because the central nervous system has its own specialized fluid, which is like plasma but different from it, and it's created as being removed from it's partly plasma that's been modified by this combination of capillaries and ependymal cells, and the ependymal cells are ciliated, so as they move the cerebrospinal fluid. And then lastly, the oligodendrocytes, and they play a significant role in holding nerves and units and creating the myelin sheath. So those are all to the central. There are other cells that do similar things in the peripheral nervous system that are part of that discussion. But that's the supporting cast. So, and the Oscar goes to the astrocyte. I had to throw that in. Accepting the Oscar is me. Could be Sasheen Littlefeather, but I'm not. No Oscar historians.
Oh, she accepted for
Brando.
Yeah, Brando.
He made an offer she couldn't. So and she gets up, and there was some question now as whether or not she actually was Native American or just getting up there, but that's a whole thing in and of itself. And the Academy was stunned. So astrocytes, abundant, versatile, highly branched, star-shaped. That's where they get their name. They're very clingy. They cling to nerves and wrap around them, and they cling to the capillaries. And that's how the blood-brain barrier works. It's got two significant components. The capillaries, and if you go back to anatomy, are what are called continuous capillaries. Most continuous capillaries look like they're all together, but they have teeny tiny openings that water and other products can get through. These have an abundance of tight junctions, so there's not a lot of openings. There's so many tight junctions. They really make it what tight junctions do, watertight. So water-soluble particles and electrolytes can't get through. The only way they can get through is through the membrane, through the astrocyte, and then through that membrane into the nerve cell. So it really limits the things that we can use to interact chemically with the brain. Read that as antibiotics or psychoactive substances, psychotherapeutic agents, medications that we use to treat somebody with depression. Probably the category that we use the most of them for. So they're very clingy to nerves, synapses, and the capillaries. They play a supportive, so they're everything. They hold them, they play the exchange role, they play developmental role, they play controlling or limiting things that can come in the environment. They do respond to impulses and transmitters. They do impact the function, and they do play a role in information processing. So when there's damage to those, it's very, very severe. So you will see them, and you always see this illustration. The yellow is the nerve, the red is the capillary. You can see all the star-shaped, and so it's almost like something leaves the capillary through its membrane, into this membrane, through this appendage, into the nerve, same way, exiting through membrane and entering through membrane. Oh, it's a long way to go for my Prozac to get to me. Said, sure, I had to go through 3 astrocytes today. I demand an inquiry. Microglial cell. They're tiny. Thorny processes are something we see characteristic of white blood cells. Lots of processes to sample the environment and latch on to things. So they touch and monitor, migrate towards areas of injury, and the injuries occur all the time in any tissue. Doesn't matter. Most of our repair work we do is pretty SOP. You know, little passageways get injured, we remove debris. If only Pennsylvania would take a clue for its roadways. It's like in the body, we don't see a lot of potholes. It's like I went out yesterday with the weather report, ran over to Home Depot to get more pet-friendly stuff for the walk. More expensive. You can transform to phagocytize, etc., etc. That's kind of what they look like, nothing special. Ependymal, squamous to columnar, they're very much epithelial cells, ciliated, that's how they circulate cerebrospinal fluid. We see them in the ventricles, those fluid-filled cavities that are part of that hollow neural tube, permeable barrier between the cerebrospinal fluid in the cavities and the tissue fluid bathing the cells. Okay, so they're part of this, and classically you'll see this. And when we see these little, what are called choroid plexes, then you're going to see these little capillary loops that are covered in these lining cells, and that's really where the finalization comes. And the oligodendrocytes are more interesting. They're not individual. You have to take a look at it. It's as though an oligodendrocyte wraps nerve fibers, really the axons, insulating the myelin sheath into thicker nerve fibers. And what's interesting, you have a cell here, and see when we look at the other ones in the peripheral nervous system, we're going to look at what are called Schwann cells. Schwann cells are individual cells that sort of jelly roll wrap around an axon, one at a time. This wraps similarly without the nucleus in the jelly roll, but it wraps around multiple nerves, because in the brain, you don't have a lot of space. So cells have to be able to really make it such that you can get a lot of bang for your buck. So the cell can latch onto multiple structures. We don't have the room that we have internally or in extremities. Okay, so that's the unique factor. Here's what we know about the ones that are in the peripheral nervous system, even though they're equally, and again, the way I phrase a question, in the peripheral nervous system or in the central nervous system, that first part of the question, you better underline PNS or CNS, because your answer may be different. What makes myelin sheath in the PNS? Schwann cells. In the CNS, oligodendrocytes. That's how students, Schwann cell, myelin. Not in the central nervous system, it's oligodendrocyte. Same stuff. Now, satellite cells, for years, we didn't know what they did. Now, they think they play a similar role to astrocytes. The Schwann cells, often called neurolemmacytes, surround peripheral nerves individually. So there's multiple ones in a long nerve, like a sciatic nerve. You'll have an amazingly large amount of Schwann cells, very similar to the oligodendrocytes, vital to regeneration. This is an important nugget. Now we know that they play a pivotal role in how the axons can regenerate, not the cell body, not the area of the nerve where the quote unquote nucleus of the nerve is. It's here. So you see it, it's a good illustration. This would be a typical sensory nerve called a unipolar nerve. Sensors would be here like in your skin, your fingertips. Come up here, the ganglion where these cluster is before it enters the spinal cord, let's say over here, would be surrounded by some of these satellite cells. And so these are the Schwann cells. All, if you go back and look at here you see little gaps. Now we call them myelin sheath gaps. It has to do with why myelination accelerates the signal, why myelinization makes them faster, because the signal effectively jumps, if you want it. And that's not really true, but it's in the old days we used to call it saltatory. We still do. It's saltatory or jumping. So that wave that we see in the muscle that goes here, effectively the nerves is more or less what they think jumping, but it's really not how it happens, and we'll get to that. And they do play a pivotal role, as you can see there. Those sheath gaps, we no longer call sheath gaps. They're maybe in the top 5 of my favorite anatomical. They're called nodes, but they're not just any nodes. They're nodes of Ranvier. Which we say in my own neighborhood, Ranvier. It's like my kid lives in North Versailles for something. I'm in North Versailles. I'm here in North Versailles, next to McKeesport. And that's what you got over there. So how you like that, apples? All right, we'll start with the nerves next time. Goodbye. I need to get something to eat.
Me too. It's enjoy later.